Okay, so we have seen so far that we can use neural networks to find models for particular problems. So let's say that we want to represent y as a function of x, and and our function does not have many parameters, so we are fitting with a polynomial of degree 1. So let's say that this is y, this is x, this is our polynomial. There is an intrinsic uh, uh, relationship that seems to be quadratic, but our polynomial has only degree 1. So because we don't have enough degrees of freedom, we may fit this polynomial. If we now increase to degree 2, then we can make a better fitting, and if we go to degree 20, then we can uh, decrease the error, the representation error of the training data, but probably this is not a good representation of our function. And in the context of regression, this is called underfitting, optimal fitting, and overfitting. Actually, it is interesting that there is no formal definition, mathematical definition of underfitting or overfitting. So, but it is intuitive. Okay, and the same can apply to classification. So we may have very simple boundaries that separate a set of points, and then with a more complex model, we can separate better the points, or we can overfit and make a perfect classification, but at the cost of having a too complex boundary that probably it is not true. It is just an artifact of the training data we have used. When we use deep learning, typically what happens is this. So underfitting is manifested by an error decrease that is similar in the training and validation, but doesn't go too low. When we have the right amount of parameters and we are able to fit a good model, then the training function goes much lower, the validation also goes lower, but sometimes not so close to the training, and then the overfitting is the opposite. So this effect increased. So the training goes really low, but the validation saturates at some point. Okay, all these definitions are intuitive, there are no formal definitions, and what is formal is this behavior of the expected errors on the weights. So let's assume that there are some perfect weights, and for a particular uh, uh, complexity of the model. So complexity is number of layers or number of coefficients in the model, and so there are some perfect weights, and these perfect weights we have to estimate them through our gradient descent or our optimization. So we have some input data, we have some optimizer, let's estimate the weights. So if you have too few weights, probably what will happen is that you will always converge to the same solution, but you will have a lot of bias in the sense that you are not guessing the right weights. So for instance, if we come to here, if you change the input points, probably you will always fit this kind of lines, but so there is very little variance, always the same result, but you are far away from the ground truth, so that is why you have a high bias and low variance. You may add a lot of coefficients, so you are now in this regime. So in this regime, you change the input points, and immediately the coefficients will change quite a lot. So you will have a lot of variance, but your predictions, they are close to the ground truth, so you will have very little bias. So there is a well-known trade-off between bias and variance in the weights of the in the weights of the network, and there is some optimum region in which you have relatively low variance and relatively low bias. That is the region of optimal fitting. And the same can be argued with in terms of risk. And so if you look for this relationship between risk and complexity and overfitting and underfitting, there is some reasoning in terms of risk. Okay, so one possibility to try to have many coefficients but have very little variance is to regularize. So when you regularize, you have your loss function that compares what you want to predict with what you are predicting, but then you add some terms, some penalization for having too high energy of the weights. And this comes to the maximum a posteriori estimate of our observations. So given the observations that are y, we want to compute a model that approximates y. So this f of w is our model. Okay, so we want to maximize the a posteriori likelihood of observing this model given this data, and this we can apply Bayes rules. So we can just do the opposite, so compute the probability or the likelihood of observing y given the model over the distribution of models, and the same so for over the distribution of models evaluated at this model particularly, and then we divide by the probability of observing y, and this is the integration over all models. Okay, if you assume that your models are Gaussianly distributed or has some particular distribution, then that particular distribution will show up in, so this term here is this likelihood of the data observed the model. This is the likelihood term. So if you assume that there is Gaussian noise in the observations, then you can reduce this term to the standard least squares. And if you assume that there is a Gaussian distribution of the weights of the model, then this will go down to this norm of the weights, and the lambda is related to the variance of the coefficients in your a priori distribution. So in general, this lambda norm, L2 norm of the weights, that is called the Tikhonov regularization, it is related to assuming a Gaussian distribution of the weights. What if we assume any other distribution? So if you assume any other distribution, in general you will have a different penalization term, and this penalization term is somehow controlled by this lambda that has to do with what is the variance of the coefficients, or how variable those coefficients are. So you can, given one regularization, you can always make the inverse reasoning. So given this regularization, there must be some assumption on the distribution of the weights such that when I take the logarithm of the product of all the observations that I have, so this maximum a posteriori, so when I take the a posteriori likelihood and I take the log a posteriori likelihood, then it goes down to this function. It always exists. It always exists, this assumption, even if it is not one known distribution like the Gaussian in the case of the Tikhonov. And then another common regularization is the L1 norm instead of the L2 norm. The L2 norm is also sometimes called weight decay in the context of neural networks. The L1 norm is related, I think it is the Laplacian distribution, and it tends to create sparse networks in which many of the coefficients are zero and then a few of them are not zero. And this is done through some shrinkage function. And there are two flavors of shrinkage. One is soft shrinkage, in which the coefficients are not, the output coefficients are not. Okay, let's start with this, the hard shrinkage. So the hard shrinkage, it is like the identity function, but if your coefficient is small, you set it to zero. So you see, these are the different weights. If you have a large weight, positive or negative, you keep it. But if you have a small weight between -10 and 10, let's say, you set it to zero. But this creates a discontinuity, because you will only have weights that have values -30 to -10, and then you have a gap. No weight has a value between -10 and 10, and then again you have weights between 10 and whatever. And to avoid this discontinuity, you may use this soft shrinkage function, so that between -10 and 10 you set to zero, but below -10 you subtract 10. So -11 you would have -1, 11 you would have 1. So there is no discontinuity. So here you have a summary of the two regularization terms. This is just the definition of the two. L1 tends to generate models that are simpler and more interpretable, because many of the coefficients are zero. While on the other side, L2, because it doesn't have that constraint, tends to be able to learn more complex data. But on the contrary, L2 is not robust to outliers, L1 is much more robust to outliers. And regularization, this kind of regularization is not the only one that you can use. There are many others that you can use, and they are also considered regularization. So adding noise to the inputs of the network, the outputs, the weights, the gradients, the activation functions, they are also a way of regularizing. Regularizing is just a way to avoid overfitting. So if you add noise, then you cannot overfit by definition, or you can have much more data. So this data augmentation, when talking about images, it is pretty easily seen. So you have this input image, but then the output associated to this image should be the same one as the output associated to all these images, even if the vectors, the x coefficients, they are not the same. The other possibility to reduce overfitting is to reduce the model complexity. So in this graph, reducing the complexity will move you from a very complex system to a less complicated system. This is dangerous in the sense that if you reduce it too much, then you cannot learn. You cannot learn too much. Okay. Another very common way of regularizing is dropout. So dropout is used during the training, but not in the inference. So during the training, so you have some input information that is propagated through the network towards the end, so that they can be compared with the outputs, with the known outputs. But then in this propagation, on purpose, you set some of the nodes to zero. So in each one of the layers, some of the nodes are set to zero randomly in every batch. So that means that from batch to batch, the network doesn't know which ones will be set to zero, and then what it will try to do is to distribute the input information, so the useful information to represent the output will be distributed in a few edges, in a few connections, so that the information is preserved when you go to the next layer, because you don't know which ones of them will be set to zero. And how many are set to zero? There is a proportion of them, so it is typically between 20 and 50%. And in practice, this is done by constructing a matrix that is the original matrix multiplied by a mask. So this is the component-wise multiplication. So multiplied by a mask that has a number of zeros. The problem of the dropout is that it has, so you decrease, so if you have some energy here, and you set 50% of the numbers to zero, the vector has now a norm that is 50% smaller. So in practice what you do is something called inverted dropout, in which you rescale the weight matrix so that the energy of the vector is the same as the one that will be used during inference. So the dropout, the scaling is performed in the standard dropout. So there is no scaling during training. It is done at inference time, and at inference time you have somehow to account for the fact that the network was learning with vectors that had a smaller amplitude. And in practice it is not used, and one that is used is this one. So you do the scaling during the training, and at inference you simply keep the whole matrix W1. So here we have the learning rates of some and the accuracy of some networks with different number of units and different number of frames and so on, and using dropout or not dropout. So when you see that when you don't use dropout, then the network has a hard time to learn. So the classification error is much bigger. In terms of size of the error in the training, you see that it is not so noticeable, but the classification error is much bigger. So the one with larger dropout is the one that is able to learn better. And the more complex the network, so here what we are changing is the complexity. So the complexity, more complex networks can learn better, even if they are more complex and we might be doing some overfitting, but because of the dropout, this dropout helps us to learn the useful stuff rather than overfitting. There is some interesting trend in modern networks, that is having a huge network. So if you have a huge network, it has been shown that what happens is this. So it is at the beginning we have this behavior that we have already discussed, but you keep on training and training and training and training, and then this over parameterized network, a network that has too many parameters for the problem we are solving, at some point the validation, this is you can associate it to the validation error. The validation error starts to decrease again, and this has been interpreted as an interpolating regime. So at some point we have so many parameters that we are interpolating the input points, but we keep on training and training and training and training, and at some point we have an interpolating function again. So we don't lose the interpolation property, but the coefficients are somehow smooth so that it learns to generalize better. And this behavior has been observed a few times with very complex networks. Another question that we might ask is it always, so do we always need classical or traditional regularization to generalize well, so to make sure that the neural networks generalize? And this paper discusses that, and there is this post here that there is a blog in this of this article here. It discusses this problem. So do we always need regularization? And the answer is no. And the formal way to prove that was analyzing what happens with the networks. So are all the layers equally important? And they came out with a couple of operations. One of them is reinitialization, and the other one is re-randomization. So reinitialization is, okay, we have trained our network, we have converged. Now I take the weights of one layer and I reset it. So I just set them uh, to uh, the initial condition. The other one is resampling. So resampling is they have converged to a particular distribution. So now I take random numbers from that distribution. So if a layer is not too important, that layer is called is said to be robust. So the network has no or only negligible performance degradation after applying any of these two operations. The other one, otherwise, if the network degrades a lot, then it is a critical layer. And what has been shown is that, for instance, here they have a neural network with different convolutional uh, uh, layers. We have not seen convolutional layers yet, but we will see. And then some fully connected layers and a final layer that is a linear combination. There's no activation function. And then they apply a re-randomization. So, so here it is again the different layers for a different network. So re-randomization. So you see that the darker the color, the most important the layer is. So last layers are more important than the first layers, and if you reinitialize at some point, so this is the where in the training you are reinitializing. You see that reinitializing the first layer is more important than the rest. And here is again the same. So these are the training iterations, and here are the different importances. So the conclusion of this study is that not all the layers are equally important. Some of them are more important than the rest, and this importance is somehow changed over the iteration. So at the beginning, changing one layer may have a lot of impact, but at some point changing one layer can be overcome very easily. So this is it for this part, and see you in the next one.